The circulatory system is also known as the cardiovascular system, and it includes the blood vessels, the heart, as well as the lymphatic system. The major functions of the circulatory system are transporting blood gases, oxygen, carbon dioxide, nutrients, hormones like insulin and growth hormone, waste products like urea. The circulatory system also functions to distribute heat throughout the body, and that helps to regulate body temperature. The circulatory system, through white blood cells, helps to protect against pathogens. These are disease-causing organisms like bacteria, viruses, and parasitic worms. So we're going to look at each of the components of the circulatory system, one after the other, beginning with the blood. The blood is a type of connective tissue in which the connective tissue cells, the red cells, the white cells, are suspended in a liquid matrix called plasma. The blood is very thick, and the word we use for thick is viscous. So within the body, there are about 5 liters of blood. That obviously varies depending on one's height and weight. But 5 liters of blood would be somewhere around 1.5 gallons, just to give you a sense of how much blood there is in the body as a whole. If we look at the components that make up blood consists of 2 major components, the formed elements and plasma. So we'll talk a little bit about the formed elements. They're the cellular components of blood, and they include the erythrocytes, which would be your red blood cells, sometimes just called red cells. Erythro as a prefix means red, and cyte as a suffix means cell. In addition to the red blood cells, we've got the leukocytes, and those are the white blood cells, often just called white cells. Leukocytes can be spelled with a C or a K. Either is okay. And in addition to the red cells and white blood cells, there are fragments of cells that are part of the formed elements, known as platelets or thrombocytes. In addition to the formed elements, we have blood plasma. That's the fluid component. So plasma is a water-based solution, and water-based solutions are known as aqueous solutions. And solutions are made up of a solvent and a solute. So the solvent is the dissolving medium, and in all the fluids or solutions that we'll be talking about, the solvent is going to be water. And then you've got chemicals dissolved in the solvent. Those would be the solute. And the solute would consist of salt ions and a variety of organic nutrients like glucose. So if we have a solution of salt water, the water is the solvent. That's always going to be the case. And the salt ions in this case would be the solute, like sodium ions and chloride ions. And if we were talking about sugar water as a solution, then water would be the solvent, and the sugar that we've dissolved in the water would be the solute. So I want to introduce the concept of the hematocrit, which I'll abbreviate HCT. The hematocrit is also known as the packed cell volume, or PCV. And the hematocrit is the percent of whole blood, a sample of whole blood that's made up of red blood cells. So there's a procedure that one uses in a lab setting to determine the hematocrit. You take a test tube filled with whole blood that you've taken out of a person's body, and then you put the test tube with the whole blood in a device called a centrifuge. And you spin the test tube around in the centrifuge, and that separates out the components of blood so that the heavier components settle to the bottom and lighter components float on top. When you centrifuge whole blood, then here's what happens. So we take whole blood, spin it in a centrifuge at like 12,000 RPMs for 3 to 5 minutes. And what we end up when we take the tube out of the centrifuge is the separation of blood components on the basis of their mass. So all the red blood cells settle to the bottom, and this percentage of red blood cells as a percentage of the whole is the red blood cell fraction, which is known as the hematocrit. And the red cells make up about 45% or so on average of whole blood. So the hematocrit in that case would be 45%. Right above the red blood cell fraction is what's known as the buffy layer, and that's a layer that's kind of a tannish brown and is made up of white cells and platelets. The white cells and platelets together make up less than 1% of whole blood. And then finally, floating on top would be blood plasma, and it makes up somewhere around 55% of whole blood. The hematocrit refers to the percent of red blood cells in whole blood. And in this case, it would be a hematocrit of 45. So the hematocrit is given as a percentage of red cells. And in males, the hematocrit ranges from 41 to 50%, with an average of around 45%. And in females, the range of the red cell fraction would be 36 to 44, with an average of somewhere around 40 for females. I'll be using these symbols fairly often. So this is the universal symbol for male, and it represents the shield and spear of the Roman god of war, Mars. And this would be the universal symbol for females, and it represents the hand mirror of the goddess Venus. She's the Roman god of love and beauty. So when we break plasma down, we find out that plasma is an aqueous or water-based solution. It's probably 92% or so water. And then dissolved in the water would be the solute, consisting of plasma proteins primarily, along with a variety of other dissolved solutes. So there's several plasma proteins that you'll need to remember, and they include albumin, which makes up about 60% of all plasma proteins, and it's the most abundant plasma protein. It's synthesized by the liver. And then we've got some blood clotting proteins that we'll be talking about, fibrinogen and prothrombin, and they too are synthesized by the liver. So these would be proteins that are dissolved in blood plasma and circulate within the blood at all times. They're known as plasma proteins. These are just some examples. There are others. We've also got, in addition to the plasma proteins, some additional dissolved solutes, like salt ions. Salt ions are sometimes referred to as mineral ions or electrolytes, and they would include sodium ions, chloride ions, magnesium ions, calcium ions, bicarbonate ions. There's a variety of different ions. And then you've got organic nutrients like glucose and fatty acids, amino acids, and vitamins, and a variety of waste products like urea and carbon dioxide for that matter. So a little bit more about the formed elements. These are, again, the cellular components of blood and include the red cells, white cells, and platelets. There is a process that occurs within the red marrow inside of certain bones called hemopoiesis. And hemopoiesis is a process that occurs in the red marrow of bone by which the formed elements are produced. So we're going to look at hemopoiesis. There are certain bones in the body where hemopoiesis occurs, and this is a partial list. Hemopoiesis occurs in the heads of the humerus and the head of the femur. It occurs inside the red marrow of ribs, the sternum, which would be your breastplate, flat bones of the skull, like the frontal bone, the parietal bones, the temporal bones, and the occipital bone. These would be examples of flat bones that are hemopoietically active. And the body or centra of the vertebral bones that form your vertebral column or backbone. When hemopoiesis occurs, it begins with cells called hemocytoblasts. Hemocytoblasts are stem cells inside the red marrow that divide by mitosis, and their daughter cells become the formed elements. So hemo means blood, cyto means cell, and blast means to form. So hemocytoblastic cells are cells that form blood cells. So this is kind of a picture showing hemopoiesis occurring in the head of the humerus. The humerus is your arm bone, and it forms a joint with the scapula or shoulder blade called the shoulder joint. So we're going to look at the red marrow inside the cancellous bone within the inside of the head of the humerus. And this then would be the inside of the head of the humerus. We know that bones are highly vascular. There are blood vessels throughout all parts of bone. So this would be like an artery entering through the compact bone wall. And then within the interior of the bone, the artery branches into arterioles, finally feeding capillary beds that are drained by venules. They eventually merge to become a vein that carries blood out of the bone. So the artery to the capillaries to the vein kind of represents the blood supply to the interior of a bone. Within the red marrow, there are cells called hemocytoblastic cells or hemocytoblasts. And the hemocytoblastic cells divide by mitosis and produce all the formed elements. So hemocytoblastic cells form cells known as megakaryocytes, really large cells that fragment into fragments of cells or pieces of cells called platelets. The platelets, as fragments of cells, are kind of roundish and flat like a plate. And the platelets, as they form, move in through holes in the capillary walls and then enter into the systemic circulation. Some of the daughter cells that hemocytoblastic cells produce are white blood cells, to include neutrophils, eosinophils, basophils, lymphocytes, and monocytes, and the white blood cells as they form in the red marrow by hemopoiesis. Enter in through holes in capillary walls and then circulate out of the bones along with the venous drainage. Hemocytoblastic cells also divide by mitosis to generate cells known as erythroblasts. Now, erythroblast is a cell that has a nucleus, but the nucleus is extruded from a erythroblast. And when that occurs, the anucleate cell, or cell without a nucleus, is now called a erythrocyte or red blood cell. And the red blood cells, as they form, move through capillary walls and enter into the general circulation. So it turns out that this process of hemopoiesis produces about 1,000 red blood cells for every 1 white blood cell. So if I had a glass container and I added 1,000 drops of red and then 1 part or 1 drop of white and stirred it around, the color would be red, because the red drops would outnumber the white drops 1,000 to 1. So red blood cells are red in color, and because they are so much more numerous as compared to the white cells, they give color to the red marrow. Hence, we call it the red marrow, because the overall color is that of the many red cells that are formed, and that would be a red color. So this is an illustration that is a little bit better than the one that I drew, but it does show the hemocytoblastic cells in the red marrow dividing by mitosis. The hemocytoblastic cells actually produce 2 daughter cells. One of the daughter cells remains in the red marrow as a hemocytoblastic cell. And that's why the hemocytoblastic cell population can maintain itself over time. The other daughter cell becomes either a myeloid stem cell or a lymphoid stem cell. The myeloid stem cells differentiate or give rise to megakaryocytes that become platelets or thrombocytes, urethroplasms that become erythrocytes, and myeloblasts that differentiate into 4 different types of white blood cells: basophils, neutrophils, eosinophils, and monocytes. We'll find later that monocytes will undergo what's called emigration and become macrophages. The lymphoid stem cells will differentiate into what are known as lymphocytes. Lymphocytes are another type of white blood cell. There's 2 types of lymphocytes that we'll be looking at: the T lymphocytes and the B lymphocytes. And we'll find later that B lymphocytes, when they interact with antigens, convert to a type of white blood cell called a plasma cell. So, just a little bit more about the erythrocytes. Urethra means red, and the erythrocytes are your red blood cells, RBCs, often just referred to as a red cell. Any reference to a red cell in the body would be a reference to the red blood cells. The red blood cells by far are the most numerous blood cell and account for 99% of all blood cells. Actually, it's even more than 99%. Within the body, there are 20 to 25 trillion red blood cells, and that's a staggering number. In fact, red blood cells account for somewhere around half of all the cells in the body. The number of red cells in a microliter of blood varies by gender. Males have more red cells per microliter of blood as compared to females. So there's a greater red cell density in males as compared to females. And for males, it's about 5.5 million red cells per microliter of blood, whereas in females, it's less than that, at somewhere around 4.5 million red cells per microliter of blood. There's around 1,000 red blood cells produced for every 1 white blood cell. So there are far more red cells produced each day and throughout life as compared to white blood cells. In fact, the red marrow produces something like 2 to 3 million red blood cells every second, and that would be upwards of 175 billion red blood cells each day. So hemopoiesis is a very active process that occurs within the red marrow of bones and produces massive numbers of cells every second of every day. A small drop of blood, just prick yourself and have a little drop of blood, would contain somewhere around 250 million red blood cells. It's mind-boggling, really. Red blood cells, as they circulate in blood vessels, are said to be anucleate. So A, as a prefix, negates something or means without. And anucleate means that red blood cells, as they circulate, do not have a nucleus. So these would be the hemocytoblastic cells in the red marrow of bone. And they divide by mitosis. Some of their daughter cells become erythroblasts. The erythroblasts actually extrude their nucleus to the outside of the cell. And the anucleate cell that results is the red blood cell that then would enter into the bloodstream. The process of red cell production from the erythroblasts through to the erythrocytes is the part of hemopoiesis known as erythropoiesis. Erythropoiesis is the formation of the red cells within the red marrow. Red cells live for about 120 days, or roughly 4 months, and then they're removed from the circulation. The primary function of red blood cells is to transport oxygen and carbon dioxide. These are what are referred to as the blood gases. So when somebody talks about the gases within the blood, they're referring to oxygen and carbon dioxide. The red blood cells are filled with a protein called hemoglobin, and I'll be abbreviating hemoglobin HB. So hemoglobin is a red-colored protein containing 4 iron-containing heme groups. So there are approximately 270 million hemoglobin molecules in each red blood cell. So I've drawn this as a representation of a hemoglobin molecule. And this right here would be the globin portion. And the globin portion is the globular protein portion of hemoglobin that's made up of many amino acids, all linked together. And embedded within the globular protein portion of hemoglobin would be the 4 heme groups. At the center of every heme group is an iron atom. And oxygen molecules combine reversibly to the iron atoms of each heme group. And that means that one hemoglobin molecule can hold or carry 4 oxygen molecules. Now, carbon dioxide and hydrogen ions will also bind to hemoglobin. They bind to the amino acids of the protein portion of hemoglobin. So I wanted to mention a protein hormone that's secreted by kidney cells when the oxygen levels in blood fall too low. This is a condition known as hypoxemia. So hypo means low, OX for oxygen, and emia refers to some condition associated with the blood. So hypoxemia is a condition in which the oxygen levels in the blood are lower than they should be, lower than normal. When EPO is released in response to a hypoxemic condition, EPO will stimulate the red marrow to step up or increase erythropoiesis, which is the production of red blood cells. So this is kind of like a flow chart that shows how this works. So we begin with a normal condition, and that would be a normal amount of oxygen and blood that's flowing through the kidney. And then we're going to experience a deviation away from normal, and that would be a reduction in the oxygen content of blood, or a hypoxemic condition. That stimulates the kidney cells to release erythropoietin into the blood. And EPO, or erythropoietin, then travels by way of the blood from the kidney into the red marrow of bone, where it stimulates the hematopoietic cells to make more red blood cells. As a result, the number of red blood cells goes up, and that increases the number of red blood cells that can pick up oxygen in the lungs and then distribute that oxygen to the cells of the body. So the increase in the number of red blood cells, increasing the capacity of the blood to pick up oxygen from the lungs, brings the oxygen levels back to normal. Now, this is an example of a homeostatic mechanism. So I want to use the term homeostasis. So let's just spend a minute talking about it. Homeostasis refers to mechanisms, generally physiological mechanisms, that maintain a stable or unchanging environment within the body. There are homeostatic mechanisms that regulate blood pressure, heart rate, your breathing rate, water balance, and a number of other physiological parameters in the body. This is an example of a homeostatic mechanism that helps to regulate oxygen levels in the blood so that the cells are getting the amount of oxygen they need at all times. It turns out that the higher number of red cells per microliter that we see in males is tied to the influence of a steroid hormone produced by the testes of guys called testosterone. So testosterone is a steroid hormone secreted by the testes, and it stimulates the release of EPO from kidney cells. And this effect of testosterone in males means that males have higher amounts of EPO in their body as compared to females. And the result is that males have more red cells per microliter in their circulation as compared to females. This means that males have a greater capacity to pick up oxygen in the lungs and then deliver that oxygen to the cells of the body, which would include contracting skeletal muscle cells during exercise. As a result, males have a physical advantage over females when it comes to sporting events that involve endurance and stamina, like running around during a soccer game, or long distance running, say marathon running, playing basketball where you're going back and forth up and down the court, and long distance bicycling, as we see with events like the Tour de France. Red blood cells are produced by hemopoiesis at the rate of around 2 to 3 million red blood cells every second. That's about 175 billion new red cells that are produced every single day. Yet the number of red cells stays constant. And that means that red cells are removed from the blood at the same rate that they're produced. So every second, 2 to 3 million new red cells form, and in that same second, 2 to 3 million red cells would have been removed from the blood. As a result, the number of red cells, because the production and the removal equal one another, stays constant over time. It turns out that old, worn-out red cells can be detected by cells that live primarily in the spleen, but also in the liver, called macrophages. And macrophages are phagocytic cells. They have the capacity to detect an old, worn-out red blood cell that's been circulating for about 120 days, the lifespan of red cells, and then eat the red cell by phagocytosis. So phago means to eat, and cyto for cell. And phagocytosis is a process by which cells like macrophages eat, in this case, red cells. So this would be a macrophage, and it engulfs a red blood cell using its plasma membrane and brings the red blood cell into the interior of the macrophage within a vesicle called a phagocytotic vesicle. Once the red cell has been brought into the cytoplasm of the macrophage, organelles called lysosomes that contain powerful enzymes fuse with the phagocytotic vesicle, and their enzymes then go into the phagocytotic vesicle and break down the red blood cell. Now, every red blood cell contains around 270 million hemoglobin molecules. In fact, sometimes red cells are referred to as bags of hemoglobin. The hemoglobin is broken down inside the macrophages as they phagocytize red cells. And I want to go over the breakdown process of hemoglobin, which occurs inside macrophages. The hemoglobin is broken down into the 4 heme groups along with the globin protein portion of hemoglobin. The globin protein portion of hemoglobin is then broken down to the amino acids that make it up. Those amino acids just diffuse out of the macrophages in the blood, and they are available as nutrients to the cells of the body, so they can be reused. The 4 heme groups are broken down to iron, and a heme group without iron is called bilirubin. The iron atoms diffuse out of the macrophages into the blood, and they can travel back to the red marrow where they can be built back into hemoglobin molecules during hemopoiesis. The bilirubin moves out of the macrophages into the blood, and it travels by way of the blood to the liver. The liver cells take up the bilirubin from the blood and put the bilirubin into a solution that the liver makes called bile. Bile travels down little tubes called ducts from the liver into the small intestine. And then the bilirubin that results from hemoglobin breakdown moves down the rest of the intestine and out of the body with the feces. So I want to talk a little bit more about the liver and its relationship to bile formation and the elimination of bilirubin in the feces. So let me just go over this illustration. So the liver is a huge organ beneath the diaphragm found in the abdominal pelvic cavity. And the liver cells pull bilirubin out of the blood and then incorporate it into a solution that the liver cells make called bile. And bile then travels down ducts that come out of the liver, and eventually the bile travels down into the small intestine. And the bilirubin in the bile then would travel down the length of the small intestine to the large intestine. It incorporates in the feces, and you get rid of the bilirubin in feces. There's a couple conditions, abnormal conditions, associated with bilirubin elimination. And they're referred to as jaundice. So jaundice is an abnormal increase in the amount of bilirubin that you find in the blood. The excess bilirubin that you find in the blood in individuals that have jaundice can leak out of capillaries and color the skin kind of yellowish and color the sclera, or the white portion of the eye, yellowish as well. So individuals with jaundice have yellow tinted skin as well as yellowish color to the white portion of their eye. High levels of bilirubin in the blood over time can result in brain damage. So it is a condition that you want to treat. There are two types of jaundice: obstructive jaundice and hemolytic jaundice. Obstructive jaundice is when you block the ducts that carry bile from the liver to the small intestine. And if you block those ducts, the liver can't get rid of its bile because the ducts are blocked. And as a result, the liver cells fill up with bile and won't accept any more bilirubin as a result from the blood. Over time, the bilirubin that's produced as red cells are constantly being broken down builds up in the blood, and this type of jaundice is called obstructive jaundice. Hemolytic jaundice is when you have abnormal rates of red blood cell breakdown. So the red cells are being broken down at a faster rate than they would be broken down normally. And that means that more hemoglobin is being broken down, and that results in an excess of bilirubin production. Another condition that I wanted to tell you a little bit about is anemia. So AN as a prefix means without, and emia, again, is some kind of condition associated with the blood. So anemia is a condition in which there are lower than normal amounts of oxygen being carried by the blood. And lower than normal amounts of oxygen being carried by the blood is due to a couple of reasons. One, there may be a decrease in the number of red cells, and the other reason, there could be a decrease in the number of hemoglobin molecules in each red blood cell. So either of these conditions will result in anemia. So the result of anemia, where blood is not carrying enough oxygen to the cells of the body, would be fatigue, shortness of breath, headaches, and you just feel kind of dizzy. There are several types of anemia. I want to tell you about 5 of them. Hemorrhagic anemia occurs due to an excessive amount of bleeding that might result from an injury. Aplastic anemia is when the hematopoietic cells in the red marrow aren't making enough red blood cells. And that can happen to cancer patients who are taking chemotherapeutic drugs. Hemolytic anemia is a type of anemia where there is an increase in the rate of red blood cell breakdown. And this can occur to someone with certain diseases like malaria. Pernicious anemia is a type of anemia that is due to a vitamin B12 deficiency. And vitamin B12, as it turns out, is essential for the production of red blood cells. And if you have a diet deficient in vitamin B12, it leads to a decrease in the number of circulating red blood cells. Iron deficiency anemia is caused by a diet that is low in iron. And this can occur, obviously, if you have somebody who is malnourished. Iron is necessary for the synthesis of hemoglobin, and without adequate amounts of iron in the diet, you have a decrease in the number of hemoglobin molecules per red blood cell, and that would compromise their ability to carry oxygen. Another condition that I want to mention is polycythemia. So poly means many, CYT for cell, and emia, a condition associated with the blood. So polycythemia is a condition where you have too many or higher than normal numbers of red blood cells per microliter. And polycythemia would be characterized by hematocrit values that would be greater than or equal to 55%. In some cases 60, 65, even 70%. The problem with polycythemia, where you have large densities of red blood cells, is that it makes blood very viscous or thicker than it would be normal, and the blood is more like molasses, like a thick pancake syrup. And as a result, it's very difficult for the heart to pump thick blood like that through miles and miles of blood vessels, and over time this can lead to heart failure and abnormal blood clots that can block blood vessels. So I'm going to tell you about a type of polycythemia that can occur as a result of excessive sweating that leads to dehydration, because the individuals who are sweating a lot are not getting fluid replacement. So this right here would be a sweat gland, and the sweat glands are lined by epithelial cells, and the sweat gland is going to open as a sweat pore at the surface of the skin. So the cells of sweat glands secrete water into the sweat gland tube, and that water moves now as sweat to the surface of the body, where it evaporates into the atmosphere. That carries heat away from the body, and sweating is a way of evaporatively cooling the body. Now if you sweat and lose water as water vapor to the atmosphere, then you need to replace the water that you lost by drinking. But it might be that you don't drink for whatever reason. And without fluid replacement, you can move the body into a state of dehydration, which can induce polycythemia. So what can happen is the water in plasma moves out into the interstitial fluid, and that's the water that moves through cells as sweat. So if you sweat a lot without replacing water by just drinking, Gatorade or a glass of water or whatever, then at some point in time, the amount of water in plasma, because it's going to be used to make sweat, will start to decline. And when this occurs, it will concentrate more red blood cells in less plasma. That raises the hematocrit and makes the blood very thick. And this can lead to all kinds of problems, particularly with young athletes who are working out in the summer without drinking water on a regular basis. So we're going to move on next and talk about leukocytes. They're going to be your white cells or white blood cells or WBCs. And leukocyte can be spelled with a C or a K. It's just personal preference. So there's about 5 liters of blood in the body. And within those 5 liters, there'd be trillions and trillions of red blood cells, because there's a lot more red blood cells as compared to white blood cells. But that doesn't mean that there aren't very many white blood cells. If you look at the white blood cells present in 5 liters of blood, there would be tens of billions of them. Not trillions like red cells, but billions of white blood cells in your body. So there's still quite a few. About half of the white blood cells, curiously enough, don't live in the blood vessels. Instead, they live outside of blood vessels in the loose connective tissue spaces within organs of the body. They live in large numbers within the spleen. You find white blood cells living in the 500 to 600 lymph nodes that are scattered throughout the body. So many white blood cells live and circulate in the blood, but they also are found in huge numbers, by the billions, outside of the bloodstream. The normal range of white cells in blood would be somewhere around 4,500 to 11,000 white cells per microliter, with an average of somewhere around 8,000 white cells per microliter. But contrast that with 5 million red cells that you'd find in the same amount of blood. If the white blood cell count exceeds 11,000, that's beyond the upper part of the white cell range, then that indicates the body is making more white cells than it would otherwise. And generally it'll do that to fight off a bacterial or viral infection. So if you find that your white cell count is really high, it's possible that your body is infected with either a virus or some kind of bacterial infection. White blood cells live for probably around 5 to 10 days. So red cells live for about 120 days, or around 4 months. White blood cells live less than that, generally around a week or so. There are some white cells that don't live that long, and there are other white cells that live for many, many years. So there's variability beyond white cells, but in general, they only live for around 5 to 10 days. Here are several functions that white blood cells carry out in the body. One is to attack and kill pathogens. Those would be disease-causing organisms like parasitic worms, parasitic fungi, bacteria, viruses. These are examples of pathogenic organisms that harm the body, cause diseases. So white blood cells are genetically programmed to be able to distinguish non-self from self. So non-self would be foreign cells and foreign chemicals that aren't normally found in the body. Non-self would be bacteria, viruses, pollen grains. Self refers to the cells of our body and the chemicals they make. So white cells will leave self alone. White cells generally don't attack and kill our own cells because they're self. Instead, white cells are genetically programmed to be able to detect and attack and destroy what's called non-self. White blood cells can clear pollen grains, which contain allergens, out of the lungs. White blood cells will move to a site of tissue damage or some kind of injury and clean up any cellular debris, dead and dying cells that might be associated with the injured site. Pyrogens. Pyro means fire, and gen means to create. So it turns out that macrophages secrete chemicals called pyrogens in response to a bacterial or a viral infection. The pyrogens are chemicals that are secreted from macrophages that travel by way of the blood to the brain and induce a fever or higher than normal body temperature. A higher than normal body temperature or a fever will inhibit the production of pathogens, and that helps the body fight off the pathogen. Emigration is a concept that I want you to know about. Sometimes it's referred to as diapedesis. And emigration is a process by which white cells can squeeze through holes in capillary walls and enter into the interstitial fluid, which would be the fluid found between the cells of the body. All white blood cells are capable of emigration. And white blood cells, as they emigrate and move through the body, move by a type of locomotion called amoeboid locomotion, sometimes referred to as pseudopodial locomotion. So this would be a white blood cell in a blood capillary, and these would be holes in the capillary wall. The white blood cell is literally capable of changing its shape so that it can squeeze through these holes and squeeze all the way out into the interstitial fluid. Once in the interstitial fluid, the white blood cell can push its cytoplasm against the plasma membrane and extend what's called a pseudopod out in front of it. And the pseudopod then will sort of grip something ahead of it and pull the cell along. And then it will repeat and do it again. And this type of locomotion that involves the formation of false feet called pseudopods is referred to as amoeboid or pseudopodial locomotion. Before I talk about the different types of white blood cells, I did want to mention just a little bit about the lymphatic system, which is part of the circulatory system. The lymphatic system is a network of lymph vessels and lymph organs, like lymph nodes. The fluid inside the lymph vessels is called lymph. It's a watery fluid very similar to interstitial fluid. All of the lymph vessels eventually drain their lymph into the subclavian veins of the systemic circuit. So, the lymph system is generally said to begin with what are called lymph capillaries. And the lymph capillaries are very permeable. In other words, there's openings in the walls of the lymph capillaries. The lymph capillaries merge to form lymph vessels. There are swollen regions along the lengths of lymph vessels called lymph nodes. Lymph nodes contain white blood cells like neutrophils and lymphocytes and macrophages. Lymph vessels drain out of the lymph nodes, and eventually lymph vessels join into the subclavian veins. So this would be blood capillary or capillary associated with the blood vascular system. And plasma is the fluid component of blood. When some of the plasma leaks through holes in capillary walls out of blood vessels, it's now called interstitial fluid. The interstitial fluid then is the fluid found between cells. If some of the interstitial fluid moves through holes in lymph capillaries and into lymph vessels, it's now called lymph. And the lymph will flow through lymph nodes and along lymph vessels, and eventually the lymph will flow into the subclavian veins, where it becomes blood plasma once more. White blood cells are found in the lymph nodes. So white blood cells that circulate in the bloodstream will emigrate through holes in capillary walls into the interstitial spaces between cells, and then the white blood cells can move through openings in lymph capillary walls and then move with the lymph and take up residence in the lymph nodes. So there are a number of different types of white blood cells, and we'll look at 5 different types of white blood cells. So the white cells are produced in the red marrow of bone by hemopoiesis. And we're going to find that the 5 basic types of white blood cells are divided among 2 major groups. The 2 major groups are the granulocytes and the agranulocytes. As we look at the granulocytes, we'll talk about neutrophils, eosinophils, and basophils. As we talk about the agranulocytes, we'll look at lymphocytes and monocytes. Now we're going to find there's two types of lymphocytes, B lymphocytes and T lymphocytes. The B lymphocytes become what are known as plasma cells that secrete antibodies. And the monocytes, after emigration, become macrophages. So let's kind of look at this. And we'll begin by looking at the granulocytes first, neutrophils, eosinophils, and basophils. So neutrophils are the most numerous white blood cell, and they make up about 60% of all the white blood cells. So 6 out of every 10 white blood cell is a neutrophil. Neutrophils sometimes referred to as phagocytes. So neutrophils are a primary type of white blood cell that attack and kill bacteria, and they also help to clean up cellular debris at sites of injury. Eosinophils account for no more than 2% of all white cells, so they're not very numerous, and they're specialized to kill parasitic worms like pinworms, hookworms, heartworms, flukes and tapeworms. These are all examples of parasitic worms that would be attacked and killed by eosinophils. Basophils are the least numerous of the white cells, accounting for less than 1%. And basophils secrete a couple chemicals that I want you to know: heparin and histamine. So heparin, secreted by basophils tonically, in other words all the time as basophils circulate in the blood vessels, is an anticoagulant. And an anticoagulant, like heparin, is a chemical that helps to prevent abnormal blood clots from forming in unbroken blood vessels. Basophils will also secrete a chemical called histamine when there is tissue damage at a particular place in the body. And the histamines will vasodilate arterioles, make the diameter bigger, and increase capillary permeability. As a result, more blood flows into the area through the vasodilated arterioles. And that's a way to ensure that you'll have more nutrients and white cells with this additional blood flow moving into the injured area. It also results in the accumulation of fluid in an injured area, which would be swelling. So typically, when you have tissue damage, the release of histamines leads to swelling that can be kind of tamped down by taking an antihistamine to reduce that swelling. So let's take a look at agranulocytes, and they include lymphocytes and monocytes. So lymphocytes account for 30% of all white blood cells. There are two types of lymphocytes, B lymphocytes and T lymphocytes, and we'll look at both, beginning with B lymphocytes, which are often just called B cells. So B cells, or B lymphocytes, are stimulated by antigens to transform into what are known as plasma cells. Plasma cells are derived from B cells that interact with antigens, and plasma cells secrete proteins called antibodies. The antibodies that are secreted by the plasma cells derived from B cells circulate throughout the body and bind to what are called antigens. And the binding of an antibody to an antigen forms what's known as an antigen-antibody complex. So just a little bit more about antigens and antibodies. An antigen is a foreign chemical or non-self. It's a chemical that's not normally found in the body. So antigens would be associated with pathogens like bacteria and parasitic worms. Antigens would be associated with pollen grains that are floating in the air and get inhaled into the lungs. Antigens are associated with what's called animal dander that can provoke an allergic reaction. Animal dander would be little flakes of skin off dogs, cats, farm animals that float around in the air and come into the lungs as you inhale. Antibodies, which are also called immunoglobulins, are glycoproteins that are secreted by plasma cells. And the plasma cells come from B cells that interact with or are stimulated by antigens. So the antibodies that are secreted by the plasma cells circulate throughout the body. They bind to antigens to form antigen-antibody complexes. These antigen-antibody complexes are important because they mark or tag non-self, like a bacteria or a viral particle or a pollen grain, for destruction. And the destruction occurs at the hands of macrophages and neutrophils that will attack anything associated with an antigen-antibody complex. And destruction occurs because antigen-antibody complexes will activate proteins in the blood called complement proteins. And complement proteins, once activated in the blood, will punch holes in the membranes of bacteria, and that kills the bacteria. So I want to just cover what happens if a bacteria gets into the body, because the bacteria would be non-self, and it would have non-self chemicals associated with its structure, and they would be the antigens. So this is a B cell, let's say in a lymph node. And this is a bacteria that might have moved into a lymph capillary and flowed with the lymph into the lymph node where the B cell is located. So bacteria on their surface possess chemicals that our cells don't make. These would be foreign chemicals or non-self. So the bacteria has foreign chemicals or non-self on its surface that would be labeled as antigens. The B cells have B cell receptors associated with their surface. And the antigen on a bacteria will bind to a B cell receptor. And the binding of an antigen on a bacteria to a B cell receptor will cause the B cell to transform into a plasma cell. The plasma cell, once it forms, will secrete antibodies. And the antibodies then will circulate throughout the body, and these antibodies will find bacteria wherever they might be found and bind to the antigens on these bacteria. The binding of an antibody to an antigen forms an antigen-antibody complex that tags the bacteria for destruction. So phagocytic cells like neutrophils or macrophages will attack and kill a bacteria that has antigen-antibody complexes attached to its surface and activate the complement proteins, which will punch holes or create holes in the bacteria that result in its death. Just a little bit about T lymphocytes. T lymphocytes, or T cells, are a type of lymphocyte that are specialized to attack and kill virus-infected cells and cancer cells that arise in our body. So we're going to leave the lymphocytes and move on to monocytes. Monocytes account for about 6% of all white blood cells. Monocytes are produced by hemopoiesis in the red marrow. They circulate within the blood. When monocytes emigrate through capillary walls into the interstitial spaces, they are then called macrophages. So a macrophage is derived from monocytes that have moved or emigrated through capillary walls into the spaces between cells. Monocytes, like neutrophils, are very active phagocytes, and they phagocytize or eat particularly bacteria at infected sites. They also help to clean up any cell debris, dead dying cells associated with some kind of injury. Okay, leukocytosis and leukopenia, two disorders. Leukocytosis is an abnormally high white blood cell count, where the white cell count is greater than or equal to 11,000 white blood cells per microliter. That's super high. It means the body is making additional white cells beyond the normal range. And that's an indication that the body is fighting off some kind of infection. It's also a situation that occurs in leukemia that I'll talk about in just a second. Leukopenia is the flip side, and that's an abnormally low white blood cell count, where the white cell count is less than 4,000, less than 3,500 white cells per microliter. And that can occur in certain diseases like AIDS. It can also occur as a result of chemotherapy or radiation therapy. An individual with leukopenia, if it goes untreated, can be fatal because you can't fight off with low numbers of white cells these bacterial infections, and they just get worse and worse and worse. So let's talk a little bit about leukemia before we move on from white cells. Leukemia is a type of cancer associated with the hemopoietic cells in the red marrow. And this is a type of cancer that results in the production of huge numbers of non-functional cancerous white blood cells. And these non-functional cancerous white cells that occur in leukemia circulate in the blood. Leukemias involve the myeloid or the lymphoid stem cells. They convert to a cancer cell that then divides uncontrollably by mitosis and produces lots of cancerous, non-functional white cells. So, there is no tumor that forms in leukemia. Instead, the cancerous cells that form in the red marrow enter into the bloodstream and circulate in the blood. The white cell count in the case of someone with leukemia, of course these are not normal white cells, they're cancerous white cells, can be somewhere around 200,000 to 1 million non-functional cancerous white cells per microliter, when the normal number would be somewhere around 8,000. So these non-functional white cells that circulate in an individual with leukemia do not fight off infections by bacteria and viruses, and all of the leukemia patients will die if the condition goes untreated. Okay, let's move on to platelets. So platelets are also called thrombocytes, and they're fragments of megakaryocytes. So one megakaryocyte that forms by hemopoiesis will fragment into about 1,000 platelets. Platelets are called platelets because they kind of look like plates. They're sort of roundish and flat, and they circulate within the blood. So if we had a microliter of blood, which is a very small volume, we'd find 5 million red cells, about 8,000 white cells, and in that microliter, we'd also find a couple 100,000 platelets. Of course, all of these collectively would make up the formed elements. The function of platelets is to form what's known as a platelet plug if a blood vessel breaks. And we're going to look at platelet plug formation in the context of hemostasis. So hemostasis is a process by which holes in broken blood vessels are plugged up to stop the bleeding. And it involves two processes, one of which is platelet plug formation. The other is coagulation. Coagulation means to form a blood clot. The platelet plug is not the same as a blood clot. There's a platelet plug that forms first, and that's followed by the formation of a blood clot. So, platelet plug formation. Platelets form what's called a platelet plug, which is an aggregation of platelets stuck together to seal up a break in a blood vessel wall, and it occurs before the formation of a clot. The platelet plug begins to form within 10 seconds of the break, and a platelet plug is fully formed within about a minute after the break occurs. I want to say that a platelet plug only forms, or should only form, in an unbroken blood vessel. The platelet plugs don't form in unbroken blood vessels. They form in broken blood vessels. So this is the process by which the platelet plugs form. It begins when you break a blood vessel as a result of some injury. And when that occurs, collagen fibers within the connective tissue in the wall of the blood vessel stick out around the edges of the break. And when platelets make contact with collagen fibers sticking out around the edges of a break in a blood vessel, the platelets grow what are called spiny pseudopods, and they become sticky. So here's a platelet that makes contact with a collagen fiber, and when that occurs, its plasma membrane juts out to form what are called spiny pseudopods. The platelets, once they grow pseudopods and become sticky, start to stick to the collagen fibers and to one another. The pseudopods will interlock together, and that helps to hold the platelets together. And the sticking of platelets to one another and to the collagen fibers collectively forms what's called the platelet plug. So here's a blood vessel, and here's a break in the blood vessel wall. And here are platelets that are circulating in blood. And when they make contact with collagen fibers sticking out from the edges of the hole, the platelets grow the pseudopods that allow them to interlock together. They become sticky and they stick together as well. And the interlocked together platelets that are sticking to one another form a platelet plug that seals up the break. This is the initial sealing up of the break, and it's followed by the formation of a stronger, more permanent solution, and that would be the blood clot. Coagulation is blood clotting, or the formation of a blood clot. And coagulation, or the formation of a blood clot, begins within 1 minute of the break, and the clot itself fully forms in maybe 3 to 7 minutes, about 5 minutes on average. The blood clot that forms consists of what's known as a fibrin mesh, and trapped in the fibrin mesh would be red cells, white cells, and platelets. So we're going to look at what's called the clotting cascade. The term cascade refers to a series of events where one triggers the next to occur, etc. Almost like falling dominoes. You knock over the first domino, and that one then knock over the next, and that one then knocks over the next. And this is called a cascade, or a cascade of events. So this would be the clotting cascade. And it begins with cells that are damaged in an injured area with broken blood vessels. And these damaged cells associated with broken blood vessels release a chemical called tissue factor. And tissue factor then activates an enzyme called prothrombinase. And when prothrombinase, which is in blood, is activated by the release of tissue factor, where you have broken blood vessels, prothrombinase converts a plasma protein synthesized in the liver from vitamin K called prothrombin to thrombin. Once thrombin forms, it catalyzes a polymerization reaction that converts fibrinogen to fibrin. Now, fibrinogen is a plasma protein that circulates at all times. It's synthesized in the liver. And fibrinogen consists of little bead-like proteins. Thrombin is going to literally polymerize or hook these little beads together into long fibrin strands. So fibrinogen is coupled together into long strands called fibrin. And then the fibrin strands collectively form a mesh, sort of like a gauze pad, that acts almost like a spider web and traps red cells, white cells, and platelets. And the fibrin mesh and the trapped formed elements together form the blood clot that then seals up the break in the blood vessels. So, I do want you to know what's meant by a thrombus. Thrombus is an abnormal clot that forms in an unbroken blood vessel. That shouldn't occur. And most of the thrombi that form in veins that are found deep down in the veins. In the legs, I mean. These veins that are found deep down in the legs include the popliteal, the tibia, the fibular. These are what are often referred to as deep veins. And when an abnormal clot or a thrombus forms in the deep veins in the legs, you get what's called a DVT, or deep vein thrombosis. Now, DVTs are kind of common in the leg veins of inactive older people who don't move around that much. Maybe those, in nursing homes. So this is especially true for people who are bedridden or sit around all day, or individuals in wheelchairs of any age. The blood clot, or the DVT, in an uninjured blood vessel can block blood flow to the tissue cells downstream. That obviously creates issues. And the DVTs can result in a PE. Now, PE stands for pulmonary embolism. So a DVT, or a blood clot in a leg vein, can split away, and the clot then starts to float with the bloodstream. When the piece of the clot breaks away and floats with the blood, it's no longer called a thrombus, it's now called an embolus. And the embolus, which is a piece of the clot that's broken off and it's floating away with the bloodstream, can then find its way up into the lungs, where it will lodge or block arteries in the lungs and result in tissue damage within the lungs. So an embolus is anything abnormal, like a blood clot, that is carried in blood and eventually goes on to block a blood vessel. So I drew a little picture here that might help to kind of see how this works. So this would be the abnormal blood clot, or thrombus, that forms in a deep vein down in the leg. It's a DVT. And if a piece of this, or all of it, breaks off and floats away, what breaks off and floats away is now called an embolus. And the embolus can float up the inferior vena cava, through the diaphragm, and into the right atrium of the heart. It'll go from the right atrium to the right ventricle into the pulmonary trunk artery, and maybe out one of the pulmonary arteries into the lungs, where the embolus, or this clot, will eventually encounter a blood vessel that's too small for it to continue to move, and it will block that blood vessel. And that can create problems delivering oxygen and nutrients to the tissue cells downstream. So there's a couple substances that I want you to know associated with clotting. Vitamin K is one of them. Vitamin K is generally abundant in the diet that comes in with green leafy vegetables like spinach and lettuce. And vitamin K is necessary for the synthesis of prothrombin. Heparin is an anticoagulant that is secreted at all times by basophils, and it helps to prevent abnormal clots from forming in unbroken blood vessels. So there's a little bit of heparin in your blood at all times. Before I finish this section up, I did want to mention the term inflammation because I intend to use it. So inflammation is the physiological response of the body to tissue damage. It's part of the healing process. It's normal. And there are 4 symptoms associated with inflammation: pain, redness, swelling, and heat. The pain, of course, comes from dead and dying cells that release pain-stimulating chemicals. The redness comes from broken blood vessels that allow red cells to escape into the tissue spaces and color those spaces red. The swelling is due to the release of histamine that increases blood flow into an injured area and causes the accumulation of fluids that results in swelling. And then heat. Turns out that when you increase blood flow to an area, you'll also raise the temperature of that area just ever so slightly, but it feels hotter than it would otherwise.